Welcome everyone to another TCS Plus talk. So for those of you who don't know or are new to TCS Plus, TCS Plus is an online seminar we've been running for now over 12 years. And we have the venue to talk about recent results in theoretical computer science. Please check out our website where every talk is recorded and we post it on our YouTube channel. So if you come across some recent result that you think will make a good TCS Plus talk, please send us a note in our website. We have suggestions and we take all these suggestions very seriously. So it makes TCS Plus a great online seminar. So today we have Aparna Gupte from MIT. Aparna is a PhD student at MIT working on the intersection of quantum and cryptography. And today she'll tell us about quantum one-time programs revisited. Before we start, I do want to make a suggestion. It's always very nice when you give a talk, an online talk especially, if people will turn their cameras on. It makes it more engaging for Aparna. And please feel free to unmute yourselves or ask questions in the chat if you'd like. Or if you don't like, there will be an unrecorded session where we get to ask Aparna some further questions. Finally, let me thank the rest of the organizers, which include Clement Kanan, Rachel Cummings, Sumega Garg, Shivam Nadimpali, and Yasmin Nazari. But with that said, I'll hand the floor over to Aparna, and please take it away.
Thank you, Eric. Hi everyone, I'm Aparna, and thank you so much for having me. Today I will be talking about this work on quantum one-time programs, and this is joint work with Jiahui Lu, Justin Drazes, Bhaskar Roberts, and my advisor Vinod Vaikuntanathan. Okay, so what is a one-time program? This notion was first introduced by Goldwasser, Kalai, and Rothblum in 2008, and it's exactly what it sounds like. It's a program that you can evaluate only once, and after that, it self-destructs. Right? So concretely, there's some program that I'll denote as a function f, and the goal is we want to compile it into a one-time program that allows you to evaluate this function exactly once. So why is this a useful notion? Well, it's a very strong form of software protection. And in particular, it implies this very powerful tool called program obfuscation. And as cryptographers, we really like this tool because it implies everything we want to build in cryptography. And finally, one-time programs are actually stronger than program obfuscation. You can get things like electronic cash or tokens that that provably avoid double spending. Okay, so it would be great if one-time programs existed, but the problem is that they're classically impossible. And the reason for this is that any classical program is just a string of bits, zeros and ones, which can be copied many times, and you can evaluate each copy separately. But, Goldwasser, Kalai, and Rothblum, when they introduced this notion, they also gave a possibility result. They said, if you had this specialized hardware device that they introduced called a one-time memory, then you get one-time programs. And, just for some intuition, because this will help a little later on, a one-time memory is this hardware device that comes hard-coded with 2 bits, B1 and B2. And you're allowed to make a query to it, a query I, and then it outputs the ith bit. And after that, it self-destructs. So given a one-time memory, GKR showed how to build one-time programs, general one-time programs, but without hardware assumptions, building one-time programs is just impossible. Classically, that is. But quantumly, there's this no-cloning theorem, that says there's no generic algorithm that takes as input a copy of a state and produces as output 2 copies of the same state. So you might hope, this circumvents the attack on the previous slide. So, does quantum no cloning enable us to build quantum one-time programs? Right? And, a little more concretely, we still have a classical program F, but now we're allowed to encode it into a quantum state that, allows you to evaluate this function F after that it self-destructs. And indeed, there's this entire field of cryptography called unclonable cryptography that leverages the quantum no-cloning theorem to build cryptography that is classically impossible. For example, quantum money, which is money that's impossible to counterfeit physically. Copy protection, software that cannot be copied and redistributed. And many other examples like unclonable encryption, secure software leasing, and certified deletion. Okay, but the question we're interested in for this talk is quantum one-time programs. And sadly, the answer is, even in the quantum world, one-time programs for deterministic programs don't exist. And this was shown by Broadbent, Gutoski, and Stebila. And the reason for this is that quantum computation is reversible. Right? So given some purported one-time program, and I'm denoting the one-time program as this ket state with the line and angled bracket around it. That's just to denote that it's a quantum state. Okay, so given some purported quantum one-time program, what an adversary could do is, evaluate it on some input of its choice, measure just the output, right? And I'll get to what this means later, but if the program was deterministic, reading this output is going to be what is called a gentle measurement, so it doesn't disturb the state. And you can reverse the evaluation and repeat the same procedure with a different input x2. So, there's really no sense in which you can get quantum one-time programs for deterministic functions. So it seems like, even quantumly one-time programs are just dead. So what next? Well, I lied a little bit. Quantum computation is reversible until you make a destructive measurement. So what that means for us is, what if we instead ask the question, can we build quantum one-time programs for randomized functions f that not only take in some input x, but also, sample some randomness r and, compute the randomized function f of x comma r. Now, if we looked at the same picture as before, when the adversary evaluates on some input x1, the program state is going to, look like this now, like a superposition over many different states. And what that means is that, there are many possible outputs because the function is randomized. And so reading this output is actually going to collapse the state to one of these possibilities, which destroys the program state. And now, the adversary can no longer reverse the evaluation and go back to its initial program state. Okay, so this attack, no longer works. So maybe one-time programs for randomized functions exist quantumly. And indeed, I will show you our construction, which, hopefully you will believe seems like a reasonable construction of a one-time program. But before that, let me quickly make sure that we're all on the same page of the notation and quantum background that we need. Okay, so classically, we represent uncertainty using probability vectors. Vectors where the one norm is exactly 1. And we act on the state of a system using stochastic processes. It's very much the same picture in the quantum land, except now the state of a system is represented as an amplitude vector, where now we care about the 2 norm being 1. And the way we act on a state is by unitaries, which preserve this 2 norm. So in this example of the state of a system, we're representing the state by this vector ket v. In quantum, we like to represent vectors with this bra ket notation. But at the end of the day, it's just a vector. And in this example, it's like 1 over square root 2, 1 over square root 2, because we're looking at the 2 norm instead of the 1 norm. And writing this out in the computational basis, this is an equal superposition over ket 0 and ket 1. Okay, and if you measure this state, it collapses to one of the outcomes with probability corresponding to the square of that amplitude. So often, quantum circuits and quantum algorithms, what they're essentially doing is they're starting with some quantum state, applying some unitary, and then performing some measurement. And for us, it'll be useful to think of this whole procedure as measuring this state V with respect to some basis that is defined by U. And another useful notion to keep in mind is the concept of a gentle measurement. So if your state was such that the outcome of a measurement is going to be almost deterministic, then the measurement is not going to disturb the state by too much. In this example, almost all of the amplitude is on ket 1. So with good chance, you're going to get ket 1 when you measure this state. And that's pretty much close to your original state to start with. Right? Okay, and finally, the last concept we'll need is that of entanglement, which is like the quantum equivalent of correlation. But here the idea is best illustrated with this example of a maximally entangled state over 2 registers, A and B. So, it's an equal superposition of either both registers being in state 0 or both registers being in state 1. And the thing that's relevant here for us is that if we measured register A and it collapses to say outcome 0, this actually also ends up collapsing register B to the same outcome in this example. Okay, so with that, let me move on to the main tool we use in our construction, which is this idea of subspace states that was introduced by Aronson and Cristiano in 2012. Here, the idea is there's some unknown random subspace S. It lives in F2 to the lambda, and it has dimension half of the ambient dimension. And so if you're given lambda over 2 random vectors from this subspace, with good chance, they're going to be all independent, and they'll give you a basis for the subspace, so you learn what the subspace is fully. What if you're given the following quantum state instead? And this is what is called the subspace state, and it's the uniform superposition over all vectors in the subspace. And I'll write it in this notation. It might look like you're giving a lot of information about the subspace because it contains implicitly all the vectors of the subspace. But what are some things you can do with this? Well, one, you could measure this state to get a vector in the subspace. And it turns out if you measure it in a different basis called the Hadamard basis, you get a vector in the dual subspace. And if you're not familiar with the Hadamard basis, you should just think of like the Fourier basis instead, in the Boolean analytic sense. Okay, so we're able to get vectors in both the subspace and the dual. What else can we do? Well, one thing we can try is, if we could take this one state and copy it many times, then we could get lambda over 2 random vectors from the subspace and then learn S fully, right? But it turns out that this state is unclonable. You cannot take a copy of this subspace state and produce 2 copies of the same subspace state. And even more strongly, given just one copy, you can't even find two vectors, one in the subspace and one in its dual. You could do either of them, but you can't do both. And these statements hold even if you're given access to these oracles OS and OS perp, which are defined as follows. OS tells me whether my query is in the subspace, and OS perp tells me whether my query is in the dual subspace. And for some intuition, the subspaces form like a very sparse set of the ambient vector space. So if I tried guessing randomly vectors in the subspace or the dual, I'm not going to succeed with great probability. Okay, but this statement says, even given both these pieces of information, the subspace state S and these oracles, I can't copy the subspace state. I can't even find two vectors, S and S perp. Okay, so these properties of subspace states allow you to build a lot of interesting crypto, in particular, something called signature tokens. So what is a signature token? Well, first, a signature is something that allows someone to verify the authenticity of a message, that a message was actually sent by the claimed sender. And a signature token is a strengthening of this notion that says, no signer should be able to sign both a 0 and a 1. So you can think of this as kind of like a one-time signature. And using subspace states, we can build this object. So the signing key is going to be a copy of the subspace state, of a random subspace state. And to sign the bit 0, I will simply measure the subspace state and get a signature, which is going to be a vector in the subspace. And to sign the bit 1, I'll measure it in the Hadamard basis. So my signature is going to be a vector in the dual subspace. And the verifier, how is it going to check authenticity? It's going to use these oracles OS and OS perp that are publicly available. Everyone has it. And it can use these oracles to check, if the message was 0, the signature better be a vector in the subspace. And if the message was a 1, the signature better be a vector in the dual subspace. Okay, so that was signature tokens. And our construction of one-time programs actually builds very heavily on this idea of signature tokens. And this should not be surprising because, signature tokens can sort of be thought of as like a one-time signature scheme. Okay, so recall our goal is to build a one-time program for a function, for a randomized function f. Maybe it takes in n bits as input, samples its some randomness r, and as output it produces f of x comma r. For simplicity, let's say n is equal to 1. So our input x is just going to be a single bit, 0, 1. Okay, so we want to use subspace states somehow, and we kind of want to play the same game as before. Given the subspace state, the adversary or like a user should be able to sample from either f of 0 or from f of 1, but not both. And how do we do this? Well, we'll also give out an oracle O. And this oracle O takes as input, the input x, but also a signature sigma of x. And essentially what it does is it checks that sigma is a valid signature of x. So if x is 0, it checks that sigma is a vector in the subspace, and if so, it outputs, a sample from f of 0, and similarly for x equals 1. And if the signature is just not valid, it's not going to output anything. Okay, so this seems like a pretty good one-time program, except that it's completely broken. And this is because, measuring this output, f of 0 comma r, is not going to destroy your subspace state at all. So in particular, what an adversary could do is, query on input x0 first and keep its state ket s in superposition. It evaluates this oracle on this query, and then once it's done evaluating the oracle, it's going to measure only this output f of 0, r. And this has nothing to do with the signature or the subspace state. So, subspace state is still intact. I can repeat the same procedure except with x equals 1 and s perp instead. And now I'll get two outputs, one from f of 0 and one from f of 1. Any questions at this point? Okay. So the idea is, if instead of making this output completely unconnected to sigma, the signature, what if instead we use the signature to generate the randomness of your sample? And we can do this by, one possibility is by taking some random oracle to extract randomness from the signature and using that as the sample's randomness. And the idea here is that now your randomness h of sigma is going to be entangled with the subspace state ket s. And so if f was highly random, measuring this output is going to destroy the subspace state. And then the adversary will no longer be able to produce two vectors, or two outputs of f. Okay, so that's our one-time program, essentially. It's the subspace state along with an oracle that checks that you're giving a valid signature to the input x. And this can be easily extended to n greater than 1 by repeating this procedure n times. So there are n subspace states now, and the oracle is now going to take n different signatures, one for each input bit, and it's going to check that all of these signatures are valid. And crucially, it's going to extract randomness from all of these signatures to produce your sample, so that you can't produce a sample from corresponding to two inputs that differ even in a single bit. Okay, so hopefully you agree with me that this seems like a good one-time program. But now the question is, it certainly cannot be a secure one-time program for all functions f. If f completely ignored the randomness, and f is just deterministic, this just cannot be a secure one-time program because that's impossible. So for what functions f is this a secure one-time program? And I guess more importantly, what does secure one-time program even mean? I've been glossing over this point the entire talk so far, but actually one of the main contributions, in my opinion, of our paper is that we give a notion of security for one-time programs that is both achievable but also meaningful and pretty strong. Okay, so with that, if there are no questions, I will move on to security definitions. Okay, so security definitions. So certainly, at the very least, some kind of a minimal security guarantee that we expect from any good one-time program is that no adversarial user should be able to produce two valid outputs given this one-time program. So for example, there's this judge who has the function f, and they compute the one-time program of f and sends it over to the adversarial user. The adversarial user should not be able to win this game, where it's not able to produce two input-output pairs x1, y1, x2, y2 that are both valid. And we say that, according to this security definition, this two output security definition, a one-time program is secure if the adversary wins with negligible probability in this game. Okay, so this is like a minimal security guarantee that we want. But it might not be enough. For example, in some settings, we might want to rule out adversaries that are able to produce, one output, but maybe half of the second output. Or in cryptographic settings, maybe the adversary is not able to produce any output, but it's actually able to win a distinguishing game on like two input-output pairs for like a pseudo-random function or something like that. Right? So in these settings, this two output security guarantee is just not enough. So whenever we're faced with this kind of definitional conundrum, cryptographers turn to the simulation paradigm that tries to formalize this idea that the adversary should learn nothing other than exactly what we want it to learn, which is one input of its choice. And so in our setting, simulation-based security would say that anything the adversary can learn from the one-time program, we could have actually simulated by querying this ideal one-time oracle. This one-time oracle, what it's going to do is answer one quantum query and then self-destruct. So this, there's a simulator here that tries to mimic the behavior of the adversary by just accessing this ideal one-time functionality. And this is how the definition is formalized, and that's why it's called simulation-based security. But a more intuitive notion of security would be, the one-time program is as good as a one-time oracle. Okay, so it would be great if we could achieve this, but it's impossible to achieve. And this is true even for randomized functions. This is also shown by Broadbent, Gutoski, and Stebila. And the idea here is like the same one as we saw before, because when the adversary is given a one-time program in its hand, we can never prevent it from making these kind of gentle measurement queries on the one-time program and on computing and then repeating many times. But on the other hand, the one-time oracle, this ideal notion of what a one-time program should be, is going to shut down after the first query, regardless of whether you were making like a gentle measurement or not.
Sorry, Aparna, I have a question.
Mm-hmm.
So would an algorithm know when it's about to make a gentle measurement versus a non-gentle measurement?
Okay, good. I will get to that in a bit. And if this is still unclear, we'll, please ask again. Mm-hmm. Okay, so, one example of what a gentle measurement could be is, this same example as before. Evaluate on some input x1. And now it's going to be a superposition corresponding to all the different randomnesses that could have contributed. But now it could make the following gentle measurement, which is maybe it doesn't measure the whole output f of x comma r, but maybe it measures some deterministic function of the output, right? And this is not going to disturb the state. So then we can reverse the evaluation and repeat with a different input x2. Does that help with the question?
I see, but for this, doesn't the adversary need to know what f looks like?
Yeah, I guess, maybe it has some auxiliary information, like some side information about what f looks like, and maybe it knows that, this function is going to be a deterministic function of the output. But, we want to ideally give a definition that's very general and secure against all kinds of adversaries.
Okay.
Does that help?
Yeah, good
Okay.
idea.
Okay, so, the issue was in the real world, you cannot prevent the adversary from making these kinds of gentle queries. But we're trying to compare it with this one-time oracle that just shuts down after the first query. And so our key idea is that we actually don't need to prevent gentle queries, especially when your function is random enough. If the function was random enough and the adversary didn't have this kind of deterministic function that it could measure on the output, the adversary is not going to learn anything useful by making gentle queries. So, the idea is, what if we allowed gentle queries in this ideal one-time oracle as well? A little more concretely, what we do is we propose this alternative definition where we're now comparing a one-time program with this modified oracle that we call the single effective query oracle. And this is not like the one-time oracle we saw before that shuts down after one query, but it allows gentle queries and on computations, just like any actual one-time program would allow you to do. So what are some properties of this SEQ oracle? It's going to allow you to make any number of gentle queries, but it's a one-time oracle. You should be able to evaluate it once. So it allows you to make at most one destructive query. And for a little bit about our techniques, the way that it records these destructive queries is by using the compressed oracle technique of Chandry's. Okay, so now let me try to give you some details about how we define the single effective query oracle. And to do this, we'll have to build up to it in a few steps. So first, forget randomized functions. Let's just build a single effective query oracle for a random oracle. And in this step, we're going to use the compressed oracle technique as a black box. And if we have time at the end, I can try to open up this black box. But even before that, let's just look at what the classical ideal one-time random oracle would look like. Just to get our bearings. Okay, so step 0. What does this one-time random oracle look like? Well, let's say Alice is interacting with this oracle. Suppose it sends some input x. What we want the oracle to do is, output h of x, or it's going to output bot after the first query. Right, the internal workings of this oracle are going to be as follows. I'm going to initialize an empty database D. And on query x, I'll check, is D empty? And if so, I'm allowed to answer this query. So I'll record x and then answer h of x. But if D already contains something, then this is not the first query that's being made, so I should not respond with anything. So the reason I wrote this out in painful detail is that now when we move to the quantum random oracle setting, where we're trying to define what like some notion of single effective query is, now we have a quantum query coming in, right? So it's going to be a superposition over many possible inputs x, and we want to respond in superposition. So in each branch of the superposition, x gets response h of x. Okay, so we could try doing the same thing as before, initialize an empty database on like an incoming query, check if the database is empty, and if so, record x and output h of x. But already we're kind of stuck, because how do you record a quantum query? Okay, so that's one problem. But the second problem is that now what if, okay, we solved that, but let's say I responded with h of x in superposition, and now Alice decides to do nothing to her program state and just returns the same query register back to me. And this actually corresponds to an uncomputation, because what Alice is trying to do is actually forgetting the output h of x. So this would count as a gentle query, and I should be able to answer it to allow uncomputation. So this means I should be able to detect whether the query is like gentle or not, right? So I should be able to check, if the current query was already queried and is the last query in the database, then I want to output h of x so that Alice is able to do this uncomputation. Okay, so both these problems turn out that we can solve them with the help of this compressed oracle technique of Chandry's. And for now, let's just think of it as a black box that solves both of these problems, and use it to define the SEQ oracle for a randomized function f that takes in both some input x and some randomness r. So on some incoming query, which is still a superposition, I'm going to use an internal SEQ random oracle as a subroutine to generate the randomness for this function f. So, I'll forward this query to HSEQ. I'll get back some randomness to use. And then I'll use this randomness to send back to Alice the output of f of x on this randomness. So, so this is like the high-level picture of what our SEQ oracle does. And this is like the definition that we propose as like a good notion of one-time security for one-time programs. In summary, we want to capture this notion that anything an adversary can do with a one-time program, it should have been able to be simulated by access to the single effective query oracle. And I sort of gave you some details of how we define it, but yeah, I did not write it down in full. Okay, and more intuitively, what this is saying is that the one-time program is as good as the single effective query oracle. Okay, so we have this definition, but why is it any good? Well, first, it's achievable. So in our work, we show that if you're allowed oracles, there is a one-time program compiler that achieves this single effective query security. And I already showed you the construction. It's this construction with subspace states and the oracle that checks validity of signatures. And two, SEQ security is meaningful. We show that if your program was random enough, and we formalize this using a notion called SEQ unlearnability, then SEQ security is going to imply this like two output security that we kind of said was the minimal security guarantee we need from one-time programs. So some examples of SEQ unlearnable functions are truly random functions, but also pairwise independent functions, and some functions that you can get from these signatures called blind unforgeable signatures. The details are not important, but some examples of SEQ learnable programs are deterministic programs. And surprisingly, even some high min entropy programs that we show in our work. And this is a nice state of affairs because on the left-hand side, there are these highly random functions that we expect to be able to produce one-time programs for. But on the right-hand side, we don't have any hope of ever producing a secure OTP, even in this like very minimal two output sense. And so this kind of suggests that SEQ security is the right definition. So in summary, we saw that this ideal one-time Oracle simulation security definition would have been great if we could achieve it, but it's impossible. So we gave a relaxation that we call this SEQ security. And we show that it's meaningful because if your function was random enough, it implies like this two output security notion that we saw earlier. But it also implies some stronger notions of one-time security, for example, for cryptographic functionalities like PRFs, for example. Okay, so I'll quickly summarize and end with an open question. In this work, we sort of reopen the study of quantum one-time programs in the setting where your function is randomized. Previously, it was thought to be, completely dead direction, but we showed that there might be some hope. And our main contribution is this definition for one-time programs that is both strong and meaningful, but also achievable. And in the construction I showed you, we had this oracle that was pretty crucial for our construction. But in the paper, we also give a plain model construction of one-time programs with no oracles for some restricted classes of functions. And we list some applications. So we get more signature tokens, something called one-time NISIC proofs, and quantum money. And I will mention this really nice concurrent work of Gunn and Mavasa. And their flagship application is generative AI. So they think of LLM queries and responses as like queries and responses to a randomized function. And so their goal is to give one-time programs for these functions as like a way to copy protect or, software, like protect software. Okay, so we give some applications and Gunn and Mavasa do, but the open question that I will leave you with is, where else can we revive applications for one-time programs for randomized functions? Before our work, at least when one-time programs were first introduced, we were mostly thinking of them in terms of randomized programs that we're protecting. So yeah, it would be great to find more applications for one-time programs in the setting where the program is randomized. Okay, and with that, I will end. And yeah, thank you all for coming, and I'm happy to take any questions.
Yep. Thanks, Aparna. So I guess we can open up the floor for a few questions, or we can also do the unrecorded question session. Okay, I'll end the recording. It seems maybe people are shy.